Hey guys, welcome back for part two of the computer assignment. I think I don't know if we did this test selection in the last part, so we'll just take a peek at that really quick. And here in our data set, we've been through all of our descriptive statistics and made sure our variables were labeled correctly. And here in StatCat, we can bring our outcome variable 10-year CHD over to the dependent variable box. And I listed in the slide the variables that we'll look at as part of this logistic regression. Our predictor variables are going to be male, age, current smoker, prevalent hypertension, and diabetes. And I just brought three of them over is what I did. And we can see that StatCat gave us logistic regression. In case we didn't take a peek at the statistical analysis steps or on the which test chart yet, we're down here on the one dependent variable, more than one independent variable graph, and we can see that for categorical outcomes, which are nominal and ordinal, that we can have any level of measurement, and so logistic regression. You should have added logistic regression to all of those columns in the nominal and ordinal rows for that table. All right, so let's go ahead and run. Well, let's see, let's just talk about assumptions really quick. Sample is randomly selected from the population. We know that from a study design. Observations are independent. We would know that from a study design. Data are normally distributed. We can check like we did with our histograms and box plots and our normality test in the descriptives. There's a linear relationship, and we talked about this in the lecture. The linear relationship is a little bit different than what it was before. Before it was between the predictor and the outcome variable, and now it's between the predictor and the log odds of the outcome. There's not much you're going to do with that right now. Just be aware that the linear relationship isn't directly between the two variables. We still have a homoscedasticity assumption. And we check that with scatter plots, and we need uncorrelated predictor variables, meaning we don't have multicollinearity between continuous variables, and no bad outliers, meaning we look for influential cases that may be impacting the model. Now we can run through our steps for our logistic regression overall. So we're going to go to in Jamovi to regression, and you see we have in the second section logistic regression and two outcomes. And our outcome variable is 10-year CHD. We'll drag that to the dependent variable box, and we'll drag male, age, current smoker, prevalent hypertension, and diabetes over. So you'll notice that I picked all of these categorical dichotomous variables, and all these were set up so that 0 means they didn't have that attribute and 1 means they did have that attribute. There's a couple reasons I did that. It makes the output a little easier to look at for right now. And remember when we were going through the descriptive statistics for many of our continuous variables, we had a lot of outliers. And to use them in regression, we probably should transform the data so that the data look a little more normally distributed. And there are ways you can transform it. Often you can take the log of the variable and it'll keep things in the same order, but make things look more normally distributed. We're just not going to mess around with that. So Age did not have any problems, no outliers. And so we'll go ahead and include age so we can talk a little bit about what the odds ratio looks like for that and some of the implications of how it's set up. All right, so we have our model overall. We need to go down to, let's stretch this out a little bigger, model fit, and we get deviance and AIC, and we want also an overall model test, and McFadden's R-squared comes up automatically, and I have never used that. We could go look it up, but I'm used to looking at Cox and Snell and Nagelkerke, so we'll get those just for fun. McFadden's is kind of right between Cox and Snell and Nagelkerke, so it's a middle of the road option. It's probably not a bad idea, but I was just used to using Cox and Snell and Nagelkerke, so we'll go ahead and keep it. All right, so for our model overall, the null hypothesis is the same as it was for multiple regression. There's no difference between the model with predictors and the null or intercept only model. And the alternative is there is a difference between the model with predictors and the null and intercept only model. So when we look at the significance test, you'll notice now we have a chi-square, and instead of an F, just from the way these things are calculated and how these are set up. So this is a chi-square test, but it is statistically significant, meaning that we would reject the null and determine that this model with predictors is significantly better than our null model that only would have an intercept. And let's move to the next slide for post hoc and follow-up. Let's go ahead and just interpret this effect size while we're here. And you'll see that the Cox and Snell is 0.077 and the Nagelkerke is 0.134. So because of the way the math works with logistic regression, you can't calculate R-squared the same way that you did with multiple regression. And so different people have come up with some different ways to estimate R-squared. And so we would just say that our R-squared lies somewhere, is estimated to be somewhere between 7.7% and 13.4% of the variance is explained. The variance in the outcome variable is explained by the predictor variables. Okay, post hoc or follow up. So we'll look at our assumption checks. And here in Jamovi, logistic regression is not quite as developed as multiple regression, so all we have is collinearity statistics, but that is VIF. And if you remember, we have this for each of our variables that's looking for multicollinearity, and values up below 5 are pretty good. 5 to 10 is a little of concern. Above 10 is definitely, you want to be looking at that and maybe changing something, but these are all down around 1, so we don't have any problems with multicollinearity here. And this is something different or new for logistic regression, and we have this prediction table down here. And let's go ahead and click these boxes for classification, accuracy, specificity, and sensitivity. And I believe next week you guys are going to be looking at a little more at sensitivity and specificity, or we did earlier in the semester. So it's good to look at, let's look at this classification table. And so observed here is in this first column, these rows. So no, meaning they didn't develop coronary heart disease. Yes, they did develop it. And then, so to get the total for those who didn't, we would add the total of these two columns for the predicted. Those are all the individuals that did not develop it. And then yes, we would add these two, and those who are those individuals that did develop it. But what we're really interested in looking at here is, so we know who developed it and who didn't, but we want to know, according to the model that we created, what did the model predict? And so of those who did not, and those who it predicted did not, we had 3579 who matched in both areas, and those who actually did develop it, and those that were predicted, it's only 19. So for those who did not develop coronary heart disease, it did a pretty nice job of predicting those pretty well, 99%, 99.6%. But for those who actually did develop the disease, it only got 19 out of 600 some odd. So it only got 2.95, almost 3% of those people correct. So this model did a lot better at identifying those who did not have coronary heart disease compared to those who actually did develop it. So not the best model out there, but and these types of things are not uncommon when you have something that occurs fairly infrequently. It's hard to come up with a good model to catch those infrequent events. And overall accuracy is 84.9 or 85%. And when we looked at sensitivity and specificity, sensitivity is detecting the thing that we're interested in. We're only down at 0.0295, but specificity is pretty darn good at up at 0.996. So just some ways to, quantify how well we classify something. Okay, looking at the predictor variables, we still have the same null and alternative hypothesis that B is equal to 0 and B is not equal to 0. So we still get the B's here, but with logistic regression, we're really not interested in creating a prediction equation because we don't. This is not a direct linear equation, and so the thing that we're predicting is a log, and it's not really that understandable to people. But we still get a significance test. We get this, what they call a Wald statistic, and it's a Z instead of a T. And we can see which are significant predictors, and we can see that all of our predictors are statistically significant, so they're all significantly different from 0, so they play a role in the model. We would look up, let's go ahead and just do our last assumption check. We don't have our Cook's distance in the assumption checks like we used to, but we still have a save model, and we can get the Cook's distance for all the individual cases. If this were a small data set, if we go over to the right side, we'll now have a Cook's distance. If this were a small data set, we could skim down and see if we could see any cases that were larger than 1. But it's not that hard to just go back to the analysis, exploration, descriptives, and put our Cook's distance in the box, and we get our number of cases, no missing values, and the thing that I'm interested in here is the minimum and the maximum. So this is scientific notation, 1.99 times 10 to the negative 6th, or I guess this is e to the negative 6th, which is moving that decimal place 6 places to the left. So it's a really, really small number. And our maximum is 0.007. So no cases were even close to 1. No problems with any influential cases. So we're there. And now effect size, let's go back to our model coefficients. And if we go to the model coefficients box, you'll see that we can get this odds ratio. So the odds ratio is the bread and butter of logistic regression. If there's one thing that you guys should just memorize and walk out of this knowing about logistic regression, it's how to interpret an odds ratio. So the odds ratio are the odds of something happening over the odds of something not happening. And so these categorical things where 0 is the kind of reference category and then 1 is the category we're looking at, then the reference the one that's on top, the thing that's referring to, has a higher odds. If the odds are above 1, then it's higher odds of having that thing happen for those individuals. If it's below 1, then it's lower odds. So if we were going to look at males, and we have an odds ratio of 1.66, then we would say males are 1.7 times more likely to develop coronary heart disease than females in this sample. And if we can look through and find the largest, and we see the largest odds ratio here is diabetes. So those with diabetes are almost 2.4 times more likely to develop coronary heart disease than others. The next highest one is hypertension. So those with hypertension are about 2 times more likely to develop coronary heart disease. The interesting one here is age. I wanted to just bring your attention to this. This is the only continuous predictor here, and the odds ratio is 1.07, which does not seem that big, but keep in mind that this is a difference for every 1 point change in the predictor variable. Now, all of these categorical variables, there's only a 1 point difference between that. They either have it or they don't. And so by default, that's kind of a 1 point difference. But here with age, this is every year. So for every year older, they're 1.07 times more likely to develop coronary heart disease within 10 years. And for 1 year, that doesn't mean a lot, but if we went 10 years, that's 1.07 times 10. Those numbers start to add up and it gets bigger. So these continuous variables, the odds ratios, you have to kind of be careful and understand how did they scale it. Here we scaled by individual years. If we went and rescaled the data so it was in decades, this number would be quite a bit bigger. It wouldn't just be single. So where there can be a lot of years, just because the odds ratio is low does not mean it's exactly low risk, because people keep aging, and so years pass and it turns into decades. So just want to make you aware of that. With continuous variables, those odds ratios may look low, but you really want to know the scale of something and how fast those numbers can progress for people, because that can make a big difference. So okay, that was looking at our variables. So what is the story the data are telling you? Which predictors seem most important? We'd say from this that diabetes seems like the most important one, that has the biggest odds ratio. Values greater than 1 for the odds means the odds increase. Values less than 1 means they're less likely, they decrease. Things are less likely to happen. We looked at some of these particular variables. Largest, second largest. How well does the model do identifying those who develop CHD? And that was pretty darn low at like 2-something% or 3%. And for those who do not develop it, it did really well. Okay, so we have had some pretty good luck reporting results for using ChatGPT to help us understand our output. So we may as well follow it through for our last test this semester and look at this logistic regression. Let me get our text here for our prompt copied. Okay, paste that in there. All right, we'll hit Shift Enter and let's go to our table here. Okay, so we've got our model fit measures. Let's click in the table, right click and go copy and Control V to paste into ChatGPT. Shift enter to go down a row. And let's take our model coefficients, right click in the table, copy, and Control V to paste. Shift enter to go down a row. Let's not worry about collinearity diagnostics. Let's go ahead and take our prediction, our classification table. I think it'll be interesting to see what ChatGPT does with that. Copy and then Control V to paste and Shift enter to go down one. And let's get our sensitivity and specificity and accuracy. All right, hit enter. Okay, a binary logistic regression was conducted to examine the effects of several predictors on the likelihood of developing coronary heart disease within 10 years. Nice, it pulled that out of that table for us. The model was statistically significant, chi-square 339, p less than 0.001, indicating that predictors reliably distinguished between individuals who did and did not develop CHD. The model explained 9.4% of the variance in CHD occurrence, McFadden's, and had an AIC of 3284 and a deviance of 3272. The AIC on its own doesn't mean a lot because we usually use that to predict or compare different models, but I won't quibble with that. The model coefficients, it reproduced our model coefficients table, and let's just for fun go see if that looks correct. 4, 2.3, 18.9. Okay, just a spot check really quick. That table looks nice, but I like the way it did that. That's nice to give to people. All predictors were statistically significant, being male, older age, current smoking, prevalent, hypertension, and diabetes were associated with increased odds of developing CHD within 10 years. For example, individuals with diabetes had more than twice the odds of developing CHD compared to those without diabetes. Odds ratio, okay. The model had an overall accuracy of 84.9% with very high specificity, but low sensitivity. The model correctly classified 99.6% of those who did not develop CHD, but only 2.95% of those who did. This imbalance suggests the model may be more useful for ruling out CHD than for identifying at-risk individuals, likely due to the low base rate of CHD in the sample and the 0.5 cutoff. Wow, you guys, I love that. I'm so impressed. I wish I had this as a student. This would have made life so much easier. Okay, so copy your report and interpretation. And let's paste that. Click in your output at the bottom so your cursor is flashing in there. Control V to paste. And there's our stuff. The table didn't come through very nicely, but we can copy the Jamovi table directly. So I'm not too worried about that. So yeah, I think that's our last computer assignment this semester, you guys. It's been fun going through these with you, and I hope some of this is making a little more sense for you, and look forward to working with all of you as you move on to your projects and get a chance to use some of these things for real. Have a good day and a good rest of your week.